Math 2312, Chapter 1, Functions, Section 1, Functions and Function Notation, Video 8, One-to-one Functions, the Horizontal Line Test. When we first defined a function, we defined it in the sense that every input has one and only one output. For any function f of x, every input x has one output y. For example, if I said f of x equals x squared, and I gave you any input like -7, there's only going to be one output. In other words, f of -7 is unique. In this case, if you squared -7, you would get 49 and nothing else. You can't say it's going to be 49, but at the same time it's going to be 8. That's what it means to be a function. Every input produces one and only one output. Now be careful, different inputs can produce the same output. What other number could I put into the function and still get out 49 besides -7? +7. When I put in 7, I get 49 and nothing else. That's what makes a function a function. One input produces one output. But if you notice, in this case, there's an output that has two different inputs. I could get 49 two different ways by putting in 7 or putting in -7. Functions can do that unless they're one-to-one. If f of x is one-to-one, then the reverse also happens. Not only does every input have one output, but every output has one input. In other words, 1x produces 1y, and 1y is produced from one and only 1x. In this case, f of x equals x squared is not one-to-one, because the output y equals 49 has two inputs. X equals -7 and x equals 7. This function would actually be called 2-to-1 because there are two x's for every one y. Well, except y equals 0, but let's overlook that one. So basically saying that a function is one-to-one makes it not a double standard in terms of x's and y's. You're a function if one x can have one y and only one y. It just so happens that different x's can have the same y. But if you're one-to-one, then that condition works backwards. Every y has to have only one x. There's another way to think about a function being one-to-one. F of x is one-to-one if equal outputs imply equal inputs. Equal outputs imply equal inputs. Meaning the only way you can get the same answer out is to put the same number in. In other words, a function is one-to-one if two different outputs, so we'll say f of x1 equals f of x2. If two things come out the same, this implies, I'm not sure if I've shown you all this double line arrow before. It's a symbol for the word implies. Actually, the symbol is a single line arrow. Double line arrow means something slightly different, but we'll stick with the double line arrow because in calculus, the single line arrow means something different. So we'll use this symbol to mean implies. F of x1 equals f of x2. In other words, two outputs are equal implies that the two inputs are equal. So the only way you can get the same thing out is if you put the same thing in. Now this function is not one-to-one because these two answers came out the same, but what went in was different. If you're one-to-one, that can't happen. How can you show something as one-to-one? Well, there's a couple of ways to do it, to show a function as one-to-one. One way is to use this alternative definition that if two inputs come out the same, then that means that the inputs were actually the same to begin with. For example, let's say I want to show that f of x equals 3x plus 1 is one-to-one. In other words, I want to show that if two things come out the same, then they had to be the same when they went in. If you want to prove that, you start by assuming two outputs come out the same. Two inputs come out the same. So let's start by assuming that we put in two different x's, x1 and x2, but they came out the same. We put in two different, and I use the word different loosely here because we're going to end up showing that they weren't different. Let's assume that two different inputs went in and they came out the same. Well, what does this function do? This function says I'm going to triple and then add 1. If I triple this, I get 3x1 plus, and then add 1, I get 3x. Let me try that again. If I triple this input and then add 1, I get 3x1 plus 1. If I triple this input and then add 1, I get 3x2 plus 1. Now I just have to see if I can do some legit algebra moves and end up with x1 equals x2. It's actually pretty easy. Subtract 1 from both sides. We get 3x1 equals 3x2. And you can probably figure out what I'm going to do next. Divide both sides by 3. All the 3's cancel, and I'm left with x1 equals x2. Since f of x1 equals f of x2 implies that x1 equals x2, in other words, since having equal inputs guaranteed that we had equal inputs, then f of x is 1 to 1. Now that's a lot of work just to show that it's 1 to 1. And there's an advantage to being a 1 to 1 function, as I'll show you in the next video. Just marking up my notations over here for the last two videos I have to do. But yeah, showing a function is 1 to 1 algebraically almost always boils down to just putting them equal to each other and then showing that the inputs were actually equal. Why was squaring not 1 to 1? Well, because setting the outputs equal doesn't guarantee that the inputs were equal. So what about f of x equals x squared? If we tried to set f of x1 equal to f of x2, this implies, because this function says square things, that x1 squared is equal to x2 squared, but this implies that if we square root both sides, we have to put a plus minus, because that's what you do when you square root both sides of an equation. All the square roots cancel and we get x1 equals plus minus x2, which was not the conclusion that we wanted. We want x1 and x2 to be the same, not have an option of either being the same or opposites. So we can conclude not 1 to 1 here, because setting equal outputs did not guarantee equal inputs. It said either the inputs are the same or they're opposite. So that's why that was not 1 to 1. But it's still a little bit of work just to show that a function is 1 to 1 by setting equal outputs and hoping to arrive at equal inputs. There's an easier way to pass judgment on whether or not a function is 1 to 1. In other words, whether or not a function has the property that if the outputs come out to be equal, then that means that the inputs had to be equal all along. That visual way is called the horizontal line test. In order to really point out the horizontal line test, I want to go back to f of x equals x squared, which we've already decided is not 1 to 1, and sketch its graph, which you may know is a parabola that opens up and its vertex is at the origin. But using the graphing technique that we used in the previous video, I forget which one it was, we could generate this graph by putting in enough inputs and connecting the dots. But this is a graph you're probably familiar with, and if not, you need to be familiar with by the time we get to the 10th and final video in the series. And if we had the other function that was 1 to 1, 3x plus 1, now we could graph this the old-fashioned way, but some of you may already know that this is in slope-intercept form. This is its y-intercept, and this is its slope. So we could plot the y-intercept, run and rise correctly to illustrate the slope. But regardless of whether or not you remember slope-intercept form, because we are going to review it in a subsequent section, this is what the graph of f of x equals 3x plus 1 looks like. Let's think about why this function failed, f of x equals x squared. Remember when we put in 7 and we got out 49? And so the point 7 comma 49 is on the graph. But negative 7 comma 49 would also be on the graph because both 7 and negative 7 squared are 49. The reason this function failed to be one-to-one is because there was a y value in output that had two corresponding inputs. That violates being one-to-one. There are two inputs to this one output. However, if we were to say 7 here, let's put 7 here, let's put 49, why not? There's only one point on this graph whose y-coordinate is 49. What's that point? 16. How did I know it was 16? I just put this equation equal to 49 and solved it real quick. But my point is, 16 is not just an x that produces an output of 49, it's the only such x. Why? Because unlike the parabola, there is no other point horizontal to this one. In other words, if I draw a horizontal line through 49, it only hits the graph once. When I did it over here, it hit the graph twice. If a horizontal line hits the graph twice, what you've located are 2 points with different x's but the same y. Or in terms of outputs and inputs, you found an output that has 2 or more inputs that can create it. Whereas if a horizontal line only hits a graph once, that means for every output there is only one input, which makes it a one-to-one function. So to summarize, the horizontal line test says this. The function f of x is one-to-one if and only if no horizontal line intersects the graph of y equals f of x more than once. The function f of x is one-to-one if and only if no horizontal line, I left out the word line, no horizontal line intersects the graph of f of x more than once. It's like the vertical line test, but it answers a different question. The vertical line test answers the question, is this equation or is this graph a function? The horizontal line test answers the question, is this function one-to-one? What's the benefit of being a one-to-one function? Well, I'll show you in the next video.